All right.
If your best mate tells you to jump off a
Here,
cliff, you're gonna do it. Like, I guarantee.
here we go. Conductor versus insulator. This is a review.
Actually, keep going.
Okay.
It's my fault for being late.
You can't like kiss up to him.
I'm not gonna kiss you. I'm just accepting that I probably.
All right. So, conductor versus insulator. The electrons in a conductor move the move the far side of the metal, of the object, okay? Versus the polarization that happens in an insulator, it does polarize, but it's just the molecules, okay? So there's still polarization, it's just in the molecules versus the entire object, okay? Consequence of that is the net electric field due to that polarization is equal to 0 on a conductor. So there are electric fields, there's just more than one. There's one from the exterior, and then there's one that's induced. There's polarization, and those two fields cancel each other out, always, in static electricity. Okay? Always, in the middle of a conductor. In an insulator, there is an induced electric field, but it's not even close to the strength of the electric field, the external one. So there still is an electric field. It's just weaker than our original one. And this is how a dielectric works. Okay. So where do excess charge is located on a conductor? Always on the exterior. If it's a sphere, it's equally distributed on the surface. On an insulator, it's wherever it was charged, stuck in that spot. Okay. So when we charge by friction, like the black rubber rod, it's just wherever you rubbed it. So if you're like rubbing it on the side and then you go with the point, it's not going to be charged. It's just going to be charged where it was rubbed with the rabbit fur. Okay. So if it's not spherical, the charges are going to congregate at points. Okay. And this is what we were learning at the end of that last unit. We have a really strong electric field here. And it doesn't really matter for an insulator, it's just wherever it was charged. Tim.
So for the conductor, didn't we have an equation to determine how like what the density was relative on those points?
Mm-hmm.
Do we have to know that for the test?
I would. And that, I think that's coming, but surface charge density over epsilon naught gives you your electric field.
I don't think that's what Tim was asking. Is that what you were asking, Tim, or were you?
No,
Are you asking for getting surface charge density?
The surface charge density based on we did like the circumference of the circle, or no? It's the radius.
The curvature. So based on a sphere, as that gets bigger. Yeah, I think that was the relationship that we boiled down, but that doesn't really do surface charge density. It does do though.
With curvature.
Yeah. So will we need to know that one for AP test?
No. Just know the fact that it points as a
So
high.
you have to calculate differences.
Okay. Yep. So said that. Mm-hmm. Not specifically. Okay. So if you're given a problem, you usually have three options. You could do what we did the first, in Coulomb's law, or electric field of point charges and summing them up. Okay.
If something
Yeah.
happens to be equidistant, it's really nice with voltage.
Okay. The shortcut is using Gauss's law. If you can come up with a symmetric surface, a symmetric field for where you draw the surface, that's really nice. Go with Gauss's law. Okay. Once you find Gauss's law, find the electric field at that certain location, and then if you're asked to find the voltage, you can integrate that with respect to distance. Remember this negative sign. Okay. Okay, so we'll get to there here in a second. Oh yeah, for this one, yes. You're gonna say wherever your initial point needs to be where your electric potential is 0. Usually that's infinity. There are some exceptions. The one being like a line of charge. Isaac.
Okay, with how can you step so I can see the equation? Okay, with how that equation is specified, as long as you know the the voltage at the initial point, that should still work.
True.
You just have to add that initial voltage.
That is true.
So it's any position with a known voltage, which just like 0 is the most convenient one to know.
Right. Because usually you're asked to find what is the value of electric potential at a certain location. That's why you want to make that your initial 0. Okay. Or you can integrate to find electric potential because it's a scalar and you don't have to worry about direction. This is true for like a ring of charge. And then you can find the negative derivative of that to find the electric field. Okay. So that's big picture strategy, how you approach free response problems. Okay. So we're going to go through all the popular shapes. Okay. Both as a conductor and as an insulator. So we have a hollow solid sphere that's uniformly charged.
On the surface.
Yep, on the surface. Okay. So if we're looking at the outside, it's just a point charge electric field for both of these. Actually, all 4 of these. And on the inside, then that electric field is 0, doing the hollow planet thing. Okay, good with that. So that's for a conductor or an insulator that's uniformly charged of a sphere. Okay. And so outside, you still get a point charge for electric potential. Inside, because the electric field is equal to 0, the electric potential does not change. So it keeps the same electric potential it had at the surface all the way through. So on our landscape of electric potential, that's a plateau. Okay, good with that? And oh, well, there it is. There's your plateau. Okay. The negative derivative of this gives us that. Okay. Good there. So that's the simplest shape. If the solid sphere is a solid sphere and it's uniformly charged throughout its volume,
It's not a conductor.
that cannot happen with a conductor. With an insulator, this becomes like digging a mine shaft through the center of the earth. Okay. So outside of this, it just behaves like a point charge. On the inside, you need to, it has a volumetric charge density. So charge of the volume of the sphere. And then you're looking for the charge on the inside of the Gaussian surface is equal to a lowercase q. That's all of this. And the volume of this sphere when you you're looking for the charge enclosed. So after you do some substitution with this ratio, you end up with this. Employing Gauss's law. Good with that? Questions there? Okay, so finding electric potential. Again, we need to draw your Gaussian surface where you're trying to evaluate the electric potential at. And figure out an expression for your electric field. Then you go from infinitely far away, usually, to some whatever location you're looking for, integrating the electric field. If your electric field has a different expression, different function, you break that up into stages. So you go from infinitely far away to whatever the point where you have a consistent expression for electric field, and then going, when it changes, going from that spot to this final location where you have a different expression for the electric field, and you add those. Okay. On a free response, they'll probably lead you to do this step and then lead you to do that step. Okay. So, electric potential on the outside of a solid uniformly charged surface, point charge out here, just like we would expect. On the inside, we got to take it from out here infinitely far away to the radius. You have a point charge here of electric field plus the electric potential going from here. So we have an expression for the electric field from here going from the radius to wherever place we're going. So we get that. Okay. And we get this as your electric field. It's linear until you reach a surface tense point charge, 1 over r squared. And then here we get the crazy, it's really just a parabola, a negative parabola. Okay. So a uniform charge ring, the easiest way to do it, in my opinion, is to first find the electric potential, expression of electric potential as a function of z, distance z. So you can do the calculus. Gentlemen, what was that?
What?
Where are you supposed to be right now?
Lunch.
Why you're not there?
Because most of the people either
Well, not out here. What were you doing? Why don't you guys hang in here and all? Have a seat back there. Yep.
What is the value? Does
I know it's kind of electric field, you have to derivate it by Z. Value.
It's just a fixed value, like it's the distance away from the ring.
Just
But like, let's say like the shape wasn't something as like nice as a ring. What if it was like a rod? What would Z be?
you wouldn't use Z.
You'd use R if it was like a. Are you saying like from the? If it was like that, you just make it like you wouldn't. You just make this like some distance X. I mean, or Z. It doesn't really matter. And you would do this like adding it up, little chunks by little chunks. Good with that?
Did you forget to account for K? That's a common mistake people make.
No, I had K.
Okay.
Was it one where you had to do 1 over 4 pi epsilon naught instead of K?
I put it in.
Okay.
All right. So you could or couldn't, like, if this doesn't come to you, you can do the calculus. If it does come to you, recognizing that all the charge is the same distance away from this point, you don't have to do calculus. Where when you do the calculus, you're like, oh yeah, that's right. This, when you plug in these limits of integration, that's going to cancel with that. Okay, so you've got linear charge density, so charge of the length, which is circumference. Okay. So once you get that expression for electric potential, then you can find the electric field by taking the negative derivative of that, which is way easier than doing the cosine, find the integral of that with the x component.
So on like the AP test, if we have a question with like a ring, if like we put down like that equation, because like we memorized it, would we get like taxed for not like writing out the calculus?
If they say derive, if they say prove, if they say something that indicates show work, yes, you would lose points. If they say what is, then no. No, there's verbiage that like will tell you, kind of indicate how much points this will be worth depending on like how much work they're looking for. Okay. So you get an expression that looks like this for electric field. There's a certain maximum that's not at the radius. Okay. And that's what you did with VPython. Okay.
Unless you were me, in which case you also got it working for not along that line.
Mm-hmm. So for a disk, we're just doing this a whole bunch of times. So we have a ring. We have that expression for the ring. We have the charge density is the charge over the area. And then the little chunk of charge is going to be this ring of charge. The area of that, you got to keep, like, this is, in my mind, this is how I recognize this is, it's got to be an area. It's got to be a meter squared. Here's your length. Here's your width. Okay. So whenever you're doing this, like, that's your safety net. Okay. You got to think of your units. Like, what? Okay, it's an area. I've got to have two things going on here. If it's a volume, I've got to have 3 cubic meters, like 3 things of meters. Okay. Okay. So, where are you going,
ICP.
Mr. Powell?
Yeah.
Okay. Is that where your buddy's going to?
No.
God, I love ICP. There's a ring of hydrogen.
Imagine like it's just the blanket.
Who would do that? Who would do something so silly?
It's just fine. What do you have a bag of candy up there? I'm really hungry. Like, when I saw that, I was just so like,
What's the bag of candy?
Danny, you're impressive to be able to sniff that out. All right.
GC, you are. Dude, I'm so hungry.
It's not going to fill you up.
All I see are the apples. That's the only food I see.
Yeah.
All right.
Why did you go to the candy instead of the apples?
All right. So, does this make sense?
Yeah. Yes.
All right. So, yeah, plug it into your calculator. Okay. Good with that? So, that's the strategy for rings and discs. Okay. The easiest strategy.
Yeah, but basically, you can't use Gauss's law. This is what you're going to want to do.
Okay. So, so integrating that, you get that expression. Or sorry, not integrating. You're taking derivative, negative derivative. Okay. Now, for a line of charge, for a coaxial cable, for any type of wire-looking thing. Okay. Even if this messes me up or messed me up, even if they give you a certain radius and you're like, hey, there's a volume there. Hey. Yeah. You have class right now?
We're in between classes right
Okay. Look, I just busted a kid.
One of my kids?
Yeah.
Doing what?
Cooking on Fastcom. You hear that? You didn't it?
Did a trash can? Howell, did you bring some for the whole class?
Let me see. Oh, no.
That's on video.
No, I don't.
Repeat it for the camera.
No. No. So this messed with me. I'm like, how do you have a linear charge density if you have a volume? Like that's where my brain went. Just hold. I think I got when I was learning this, I got tripped up by the fact that it's like there's a volume there. How can I have a linear charge density if there's a volume? The idea is this is so small compared to the length that it doesn't really matter. Okay? So your linear charge density, you can just take it as a function of length. You don't have to like distribute it as like a surface area or a volume.
So it's a bunch of points on it.
Mm-hmm. Yeah. So we draw your Gaussian surface on the outside.
Daniel, did you get a donut?
And the area, the electric field's going out like this. So the flux through this surface is 0. And so all you care about is electric field going out to that. The area of that is the circumference times the length. Okay, length being this of just your Gaussian surface. Okay, and so that's when you can incorporate your linear charge density times length is equal to the charge enclosed. Okay. So you get that expression, and then once you have that, you can integrate that. But if you go from infinity to R, things fall apart. And so this is the exception where we're going to say that the electric potential is 0 at R.
Something seems wrong with that equation. Why are there two lowercase r's in there? Shouldn't that 1 over r just end up with the ln, and you should have a 1 over r outside the integral? Or am I just missing something?
On the last one.
It's a bunch
The
of
final
numbers.
equation.
Oh.
It's a bunch of letters.
Oh.
Oh,
Yeah, that makes sense. I can delete that.
Just delete the whole slide.
That R.
That took me some.
We are not starting this again. Give it to Daniel.
So the reason you integrate from the normal radius to wherever
Daniel
it
was
is,
starting
because
on
you
the
always start
street and it
from
started
zero,
like raining
wherever
raisins.
equals zero.
If you started from the traditional way, if you started from infinity, you're gonna get in your expression, you're gonna get infinity.
Yeah.
And that's not helpful.
So you always start from wherever it's zero.
So we declared this is 0.
So you start from wherever it's zero.
Yeah.
It's a much how
You can
simple and arbitrary.
just like I can say this is ground 0.
Because you're looking for the change, not
Brad, are you going to ours? And then like yellow object.
I'm a crack.
That one.
Bro, considering how he acts was saying on that surprise.
Good at that. Okay.
Who's this really tall guy walking around campus? What's going on? None of that.
All right. So
That is not coax.
if we have coaxial cable, okay, we're employing this, what we just did. Okay. So our Gaussian surface is this.
That one's negative. That's actually just like.
Okay. Good with that? And so we're going from the inside to wherever we're going. If you go all the way out, it'd be to RB.
Why is that what you consider a coaxial cable? Why doesn't it look like those old coax cables that you would use for slow internet?
There's a lot of different designs.
What if it's greater than RB? Do we have to worry about that?
Well,
It's 0 outside of that.
No, it's
I mean,
it's not. It's
yeah,
just that it's
it
just
would
that-
be. It would be out.
Because there's one negative lambda.
Right. If that's the case, yes. If you're looking for the outside and it's not equal, you're just going to combine these two together. You're going to add these two together. And so the charge enclosed would be equal to L times the sum of your in and your out. Does that make sense?
L is greater than R.
No, the R in the integral.
And this,
So you want
it's like a really long.
It's so
Yeah.
that you can have a so that you have a uniform electric field so that symmetry works.
You good with that? And that's usually what they always give you.
Why are you just going from RA to R? Shouldn't you also go from zero to RA? Because there's much field.
You're in a conductor.
Oh, that's conductor?
Probably.
Been blue. I thought that's an
It doesn't matter. It's just charged, and we are going from. So there's two shells here. There's the inner. You can say insulator or conductor. I don't really care. And then you got a secondary. This is inside the.
secondary. Oh.
We're trying to find the electric field between the two. We're trying to find the electric field between the two and the gap between the two. Okay? Right.
Go ahead.
Daniel.
Why are you starting from RA? Isn't it zero? Oh wait.
So for a linear charge, we don't start infinitely far away. This is the exception. You start at the surface. Okay? Nope, you're good.
If I assume if the never mind. I answered my own question.
Okay.
Can you say what the answer to your question and what it was so that perhaps the
What did you substitute for Q?
I substituted. So Q enclosed to be equal to lambda times L,
So what happens to L
or capital L. That got canceled out
with the L in the area?
with the L in the area.
And Q inside in between them?
It's on this darker beige looking. I think is this.
Middle
Yeah. What? Okay. Good with that. This is definitely the weirdest, in my opinion. But it pops up often. Okay. So if we're looking for the capacitance, okay, this is the electric potential difference between this surface and that surface, where we've used this instead of, but we're going to RB. Okay. So like the whole gap here. And then we just take that. Capacitance is each. Isaac, stop.
it's more that
Isaac!
it's more that incorrect R that shouldn't be there from
Okay, just let me finish my statement. Let me finish my statement. Okay. You got charge over voltage. Okay. Isaac, I am good with you correcting. I'm totally fine with you correcting me. Just wait. Okay. Because you derail the flow of thought.
sorry.
Okay.
There's more extra R. There's two more on this slide.
Right there.
It amazes me that I can actually start so for the integral. Well, they have calories.
Bruh, dude. Wow.
You're eating cough drops? I'm coughing anyways. I'm not
Oh,
saying I would
you can die from that, you know.
I'm not gonna eat that.
All right. So here we go. 5 more slides. Let's finish this.
We got this.
All right.
Bro, think about all those goldfish.
For a plane of charge. Okay. This is not a plate of charge. This is a plane of charge. Okay, 2-dimensional. Uniformly charged, has a certain surface charge density. So we can make this shape, this Gaussian surface, anything we want to. Keep that area consistent with that area. This has to go all the way through because it has no other choice. There's no in the middle. It's 2-dimensional.
have one of the ends be on that plane,
Sure.
but then you don't know the field, and that would be more.
Okay. So because of that, you've got electric field coming out this way and this way. So you have twice the flux. Okay. So that is where that 2 is coming from. So you have twice the area. You can just leave it in terms of area. You don't necessarily need to like do like pi r squared for that. You just leave it as area. Okay. So the enclosed charge is going to be the area times the surface charge density. Okay. So I should probably just get rid of this stuff. But you got electric field times the area. There's 2 of them is equal to area over surface charge density over epsilon naught. So that's where that's coming from. Okay. And so to find electric potential, you just integrate that, going from 0 to S, meaning S being a certain distance away from the plane. Good with that? And when you do that, everything's constant. So you get this. This is where that comes from. Is the electric field constant regardless of how far you are away from an infinite plane of charge. Good with that? Then if you have 2 parallel plates, you're going to draw your Gaussian surface. One's going inside, the other one stops in the middle of the plate. So your electric field is equal to 0 here. Okay. The surface charge density changes when you bring a secondary plate. It brings that to this side. So that's what's making the field stronger from a Gauss's law point of view. From just adding up the electric fields, you got electric field from this guy, electric field from this guy, making it twice as much as this electric field here. So you get an expression of that. Okay. And this is the electric field that we use in a capacitor. Okay. And so if we were to find electric potential difference, everything's constant. You get that again. It's just a stronger electric field. Good with that? Spherical concentric shells outside. If these have the same charge, total and charge, closed charge is 0. Therefore, electric field is 0. Therefore, electric potential is 0. Infinitely far away, it's 0 all the way to here. Okay. Then inside, we're going to say the Gaussian surface is in the middle of this gap here. The enclosed charge is just this inner one, so it's the charge on the inner shell. So it becomes a point charge. Okay, because the electric field from this guy, the blue one, is 0 on the inside hollow planet. And when we go from infinitely far away, this drops out. That's 0. Then going from RB, which is in here, to some distance r, find that to be a point charge of, oh no, just kidding, don't do that. Got to go from RB, or 0, to r, and so you get this difference here. Find the capacitance. Yep, sure can.
Shouldn't the electric field from R to RA?
That's what this is. That's what, if you go all the way, that's the RA. This is just stopping before you get, it's just some random point. Like, hey, what's the electric field at some point between RA and RB?
Can you go back?
Good with that? Okay. So, because we're not starting infinitely far away for this point chart, like this gap here, like this part's 0, but this part is not. We get this expression here. If we're going all the way, going from RB to RA, you stick RA there. Capacitance, you need to go all the way to get that expression. Voltage over the charge. And those are the most popular shapes that you will see on the AP test. Okay.